G'day everyone, and welcome to our lesson, the photoelectric effect equations. In the first lesson on the photoelectric effect, the other video I did, we basically built up the conclusions of the photoelectric effect from the experiment. In this lesson, we're going to start with the equations, which I have to the top right, and look how they support the observations of the experiment. So to summarize what exactly they support, the photoelectric effect supports the particle nature of light. This is because we hypothesize that there is a one-to-one interaction between a photon and an electron. This would not be possible with a purely wave model of light, but it is possible when you think of light as a particle. So first of all, just to recap the photoelectric effect experiment, we had a metal surface here, a full circuit, that green line would extend all the way around. We positively charged this electrode and negatively charged that electrode using a battery somewhere else in the circuit. And then we shine light, preferably of a single wavelength and therefore a single frequency, on that metal surface. And that causes an electron to eject. So the blue squiggly line is the photon and the red line is the electron. The energy of the most energetic electron, so the one that was sitting presumably right on the surface of this metal, not buried deep within, but right on the surface, the energy of that electron is given by this formula here. It was the energy of the photon that struck it, take away the energy of the work function. And the work function is basically how much energy it took, first of all, for that electron to just barely escape from that metal surface. So say the photon had a lot of energy. First of all, the electron has to use up some energy just popping off. Then the rest of that energy, say the photon has a lot of energy, the electron has to use just a little bit of energy popping off, and then the rest of that energy becomes kinetic energy. So the speed of that electron increases. So whilst the energy of light is determined by its frequency, the energy of an electron is determined classically from its speed. So we talked about voltage a little bit before. We can positively charge that electrode there and negatively charge this one. If we do that, we can keep making this one more and more positive and this one more and more negative, thereby increasing the voltage, until we find that even the most energetic electron gets turned back. And that's a really clever way of finding out the energy of that most energetic electron, because the voltage and energy are related. So let's discuss that now. My starting point is that the stopping voltage, the voltage at which you get no electrons reaching this electrode, so the voltage at which the even most energetic electron is turned back, is another way of describing the kinetic energy. Now normally, we describe kinetic energy in terms of joules. And a joule is a Newton meter. But there is a second way of describing kinetic energy, and that is the electron volt. And the electron volt, I won't write this down, I'll just voice it. It's the amount of energy an electron receives, kinetic energy that it receives, when passed through a single volt electric field. So if my stopping voltage here is 4 volts, then that means an electron that was starting here with a lot of energy must lose 4 electron volts trying to get through that field. So if my stopping voltage was 4 volts, that means the energy of the electron, the kinetic energy of the electron, is 4 electron volts. So V naught equals kinetic energy in electron volts. If you want to go from electron volts to joules, you have to multiply by 1.6 times 10 to the negative 19. And if you want to go from joules to electron volts, you have to do the opposite. You have to divide by 1.6 times 10 to the negative 19. So electron volts to joules, multiply by 1.6 times 10 to the negative 19, and joules to electron volts, divide by 1.6 times 10 to the negative 19. So that's how we describe the energy of the electron. So here, these two equations here are the same thing. The energy of the electron can be described in terms of the stopping voltage. And the energy of the electron is the stopping voltage in electron volts. Now, the work function is a constant. We don't describe that by anything except W for now. But the energy of the photon certainly can be described. To find the energy of a photon, say you know its frequency or its wavelength, you can say the energy of that photon, is equal to this Planck's constant multiplied by the frequency, or, since frequency equals c on lambda, the speed of light divided by the wavelength, hc on lambda. And that's why we have these up here. So, if I know the energy of the photon incident upon the metal surface there, and I know the work function, all I have to do is say the electron will have all the energy of the photon in terms of kinetic energy here, except that energy that was used up popping off the metal. So I have to take away W. Likewise, if I know the kinetic energy of the electron, then I can E electron plus the work function must have been the energy of the photon. So I can rearrange that equation there. Let's see how this major equation here supports some of the graphs we looked at in the first video. So there are two key graphs. The first of which was a graph of photocurrent versus voltage. And the graph looked like this. Say we were using blue light here. It looked like that, but it tapers off a little, so like that. And that's saying, if we took the voltage to this level here, we got no more electrons flowing through. And that describes the situation I drew before. Even the most energetic electron being pushed back by this negative charge here and this positive charge here. So this corresponds to the stopping voltage. And then if I increase the intensity of that blue light, there, the energy of the most energetic electron doesn't change. Because over here, we see the energy of the electron is determined by the work function and the frequency. Increasing the intensity of the light does not necessarily increase the frequency. It simply means there are more photons incident upon the metal at a given time. So if the stopping voltage can't change, the graph has to still intersect here. But the photocurrent quickly rises above the level it used to be, because more photons means more electrons actually being ejected over here. Furthermore, say I lower the frequency of that light. The stopping voltage will decrease there. So we're saying decrease in magnitude, not in absolute value, or not in terms of negatives and positives, just decrease in magnitude. So say I had, we'll say yellow light incident upon this metal here. The stopping voltage is a lot smaller. There we go. So we'd have a graph that looks like this. Now here's a bit of a trick question. This line here represents blue light of higher intensity than this line here. If I shine yellow light upon the metal with the same intensity as that blue line there, this is what the yellow line would actually look like. It would climb up and then it would go over that blue line there. So, with the same intensity, yellow light creates a larger photocurrent than blue light intensity. And this is a bit of a detour, but I think this is quite interesting. This is what high intensity blue light looks like. So we've got, say, two photons coming in, both with a lot of energy on some kind of surface. If we want to have the same intensity yellow light, we want the same total amount of energy, but we know, since the frequency of the yellow light is lower, the energy of each photon will be lower. So it's like firing two very fast cannonballs from one pirate ship to another. If you want the same amount of energy, You only have to fire 2 of those fast cannonballs. But if you then take a slower cannon out and you say we want the same amount of energy, you might have to fire 3 slow cannonballs at a time to get that same energy and that same intensity. So these 2 blue photons here can only really eject 2 electrons, but these 3 yellow photons, even though each has a lower energy, they can eject a total of 3 electrons there. That's why this line is a little bit above blue. And then if I get a higher intensity yellow light, it'll look much the same up there. That's something to keep in mind. It is a trick on some exams. So that's why we see this graph here. Whoops. The only way to change the stopping voltage isn't to increase or decrease the intensity of the light, it's to change the actual frequency. Let's look now at the other graph. That's a graph of stopping voltage versus frequency. And we said before, there was a threshold frequency. And what the threshold frequency basically is, it's a photon that comes in that gives the electron just enough energy to get off the metal, but not enough energy to have any appreciable velocity across that gap there. So it basically means the kinetic energy of the electron is 0, and the energy of the photon was pretty much equal to the work function. So HF equals W, F equals W on H. That is what's known as the threshold frequency. I'll move this aside. So if I go ahead and sketch my graph now, say for this metal we have up here, we have a threshold frequency here. That's the first frequency at which we have any kind of stopping voltage. And then as I turn up the frequency of the light, the stopping voltage increases. You can see that relationship up here. This looks a lot like y equals mx plus c, which is a straight line. As frequency increases, the stopping voltage increases linearly. So it looks like that. This we said here was the threshold frequency. And if I extend the dotted line below the 0 point for the stopping voltage, this length down here is equal to the work function. That's just a perk of this straight line graph. If I change the metal surface to a metal surface with a smaller work function, smaller in terms of absolute value, then you'd expect it to intercept there. And you get a dotted line here, and then a straight line here. So if I change the metal surface, change metal surface to something with a smaller work function, or in other words, that binds its electrons less tightly, as you would expect, I can still get electrons off with lower energy photons, so photons with a lower frequency. So this straight line graph is in fact just a graph of this equation here, and I can adjust the work function to shift this graph up and down, because this is like our C term, which we'd see in math methods. Let's look at a few example questions to see how this kind of thing can be applied. I'll leave this picture up here. So, I've got a metal with a work function of 2.2 electron volts. And I want to know what is the minimum frequency of light needed to eject an electron. So I'm asking about the threshold frequency. Well, we know the threshold frequency is the frequency that gives an electron of practically 0 energy. So 0 is equal to E photon, take away the work function, which is equal to HF take away 2.2. Since we're dealing in electron volts, I'm going to select the Planck's constant, which is in electron volt seconds. So being a good physics student, I'm going to get my unknown by itself before I solve. This is add 2.2 to both sides. 2.2 over 4.14 times 10 to the negative 15. That's dividing both sides by Planck's constant equals F, and that's F naught. And if you solve that, you get F naught equals 5.31 times 10 to the 14, and frequency is in hertz. So given a work function, you can figure out the stopping or the threshold frequency. Question number 2. This same metal surface, so work function equals 2.2 electron volts, has light incident upon it of frequency 9 times 10 to the 14 hertz. Notice straight away, this frequency of 9 times 10 to the 14 hertz is above the threshold frequency. So if I sketch V naught over the frequency, if here's the threshold frequency, I'm selecting another frequency here, we're expecting some kind of kinetic energy straight away. This frequency will eject an electron. So work equals 2.2 electron volts, the work function. Frequency is 9 times 10 to the 14 hertz. And we want to know what is the maximum kinetic energy in joules that this light will eject from this metal surface. So we say the energy of the electron equals the energy of the photon, take away the work function. Energy electron equals the energy of the photon, where we say H, F, take away W. Since W is already in electron volts, let's work in electron volts for now. So that's 4.14 times 10 to the negative 15 multiplied by 9 times 10 to the 14, take away 2.2. I have that down here as 1.526. So we'll say 1.53 electron volts. I'll just check that now. Yeah. And since we wanted it in joules, to go from electron volts to joules, I've got to multiply by 1.6 times 10 to the negative 19. Which is equal to 2.44 times 10 to the negative 19 joules. So if I shine light of frequency 9 times 10 to the 14 hertz upon a metal with work function 2.2 electron volts, the kinetic energy in electron volts of an electron that pops off is 1.53, and the electron energy in joules is 2.44 times 10 to the 19 joules. And I should mention again, this is kinetic energy in that electron. Final example question. Say I have light with a work function. No, we won't say that. Let's find the work function. Light shines upon it of wavelength 400 nanometers, and an electron pops off with kinetic energy 2 electron volts. Let's figure out the work function. So first of all, we use this relationship here. V naught is equal to EK is equal to, so 2 is equal to H. We won't use HF, we'll use HC on lambda since we do have lambda. Take the work function. So to get the work function by itself, W equals HC on lambda, take 2, which is equal to, we'll get the work function in electron volts, I think. Electron volts. So this is equal to 4.14 times 10 to the negative 15 times 3 times 10 to the 8, that's the value of c in a vacuum, divided by, sorry, that's the speed of light in a vacuum. The value of c is always 3 times 10 to the 8, divided by 400 times 10 to the negative 9, take away 2. And I have this as 3.1 take 2, which is equal to 1.1 electron volts. And if I wanted the work function then in joules, I have to multiply by 1.6 times 10 to the negative 19, and I have the work function come out as 1.76 times 10 to the negative 19 joules. So I hope that helps you understand how you can manipulate these equations to figure out any one of these variables. So we have kinetic energy, frequency, or work function there. And the frequency can be related to the wavelength there, so you can also find out lambda. The number one thing to take away is that the photoelectric effect, unlike Young's double slit experiment, supports the particle nature of light. And you may be asked to explain why it does. You have to mention that it indicates there's a one-to-one interaction between the electron and the photon, which is why you get that threshold frequency where no light below a certain frequency does eject an electron, and also why increasing the intensity of the light does not increase the max kinetic energy of the electrons.